Okay, here we are for video 2, starting on number 10. Number 10. The rational function h is given by h of x equals to all of that there, which the following describes the end behavior of h. So end behavior is again a horizontal asymptote. Looks like we have a fifth degree over a second degree. So a fifth over a second degree, which means there's going to be no horizontal asymptote, which means the end behaviors will be going to infinity, which means that we should having end behavior where the top dominates. So that's an odd positive. So we should be going up in that direction and down in this direction. The end behavior should look something like that there. So this says as x increases without bounds, so as x goes to infinity, h of x increases without bound. So that would mean that h of x also goes to positive infinity. That is correct. As x decreases, so as x goes to negative infinity, h of x also decreases. Goes to negative infinity as well. So that should be correct, but let's check these other ones. As x increases, h of x increases. That's true. As x decreases, h of x decreases. So it's not that one. As x increases, decrease. Nope. There should be increase, increase, decrease, decrease. And then as x increases, h decreases. Nope. So it's got to be A. Got to be A. Number 11. The polynomial function p has 3 distinct zeros with a multiplicity of 1. And its leading coefficient is positive. So 3 distinct zeros. So if I wanted to write this out, we got x minus a, x minus b, and then x minus c. So there's my 3 distinct zeros with multiplicity of 1. The polynomial function q has exactly 1 zero with a multiplicity of 3. So this is p over q. So q has 1 0. We'll say x minus d with a multiplicity of 3. And its leading coefficient is negative. So this would be a negative. The rational function h can be written as, okay, p over q. We got that, p over q. Which of the following statements about h must be true? So this is a third over a third. So we're going to do third over a third, and it's asking about end behavior, horizontal asymptotes, end behavior. So third over a third degree over third degree is going to be coefficient over coefficient. So this should be a some number. I don't know. We haven't used f yet. We'll make it f over the leading coefficient here, which is negative g, whatever. And so this is going to be some negative number. So has a horizontal asymptote at y equals 0. Nope, because the degrees are even. Has a horizontal asymptote at y equals a, where a is bigger than 0. Nope, this is what a would be. It's negative. It should be less than 0. And that's it right there. 11 is C. This one you can use a calculator for. The rational function r is given by r of x equals that. Little calculator icon, by the way, if you didn't notice. For what values of x does r of x equal 0? So we need to find when does r of x equal 0. So we have 3 zeros on top, so we should have at least 3 possibilities at most. Can I factor this? I cannot factor it. Then I can think, nope, I do not see a way to easily factor it. This bottom one, I also don't see an easy way to factor it. So I don't have my calculator here, I don't think. So I might just have to go type this into Desmos real quick. But you can use the zero function on your calculator to find the zeros here. So I have x to the third minus 4x x to the third minus 4x plus 3 over x to the fourth plus 2x minus 4. And we have, oof, that's a weird looking graph. But we should have a 0 at negative 2.3-ish. So negative 2.303. So that's a 0 here. So that one's good. Which was that one also, that one also. Check the next section has a 0 at exactly 1. So that's good. That one's good. And, oh, right here. And then the next 0, check that one. It's going to be at 1.303 positive. So can't be A, can't be B. 1, 3, 1, 3. So this one has some extra ones. It's a third power on top, so it can't have more than 3 zeros. So it must be C. Must be C. Okay, 2 more. In the xy plane, the graph of the rational function f has a vertical asymptote at x equals 4. Which of the following expressions can define f of x? So if you have a vertical asymptote at x equals 4, that means in the bottom of the function, we should have an x minus 4 down here that doesn't cancel out. So we need an x minus 4 that doesn't cancel out. So let's see here. On my first one, that is an x plus 1. So these are the same. That cancels out completely, and 2 of those will cancel out. Here, x minus 4, and we can rewrite this now as x plus 1. These 2 canceled out. Times x minus 4 squared over, I'm going to factor out a negative here, and then do it 3 times to the third power. So if I factor out a negative 1 to the third power, I can make this x minus 4 to the third, and then negative 1 to the third power is just negative 1. So these 2 cancel out, leaving just 1 down here. Okay, that could be it. So that does leave an x minus 4 in the bottom, then just one of them. So it could be that one. Here we do the same thing. That cancels out. Here, oh, both of these would cancel out this time. So this one wouldn't work. We need more x minus 4s in the bottom. Down here, see, we have less x minus 4s in the bottom, so that's going to leave 1 on the top, so it can't be that one. And then here I have no x minus 4s at all, so it can't be that one, so it's got to be A. 14, the rational function g is given by all of that, and they factored it for you. At least they start. Here it won't factor again. This one we can factor as x plus 10 times x minus 10. So there is a difference of squares you can factor out of that one. Which of the following statements describes the behavior of the graph? So the graph intersects the x-axis at negative 10. So it would intercept at negative 10. Oh wait, no, it wouldn't, because these would cancel out. There's a hole at negative 10. So negative 10 will not work, so it can't be A. Because because this should be a hole, not an x-intercept. The graph has a hole at -10, correct, because x plus 10 appears exactly once in the numerator and exactly once in the denominator, correct, when both the numerator and denominator of g are factored. So yeah, that's a contender, could be this one. Let's check these other ones just in case. The graph has a vertical asymptotes at x equals 10 and x minus 10, because 10 squared minus 100. So these are both excluded values, but only one of them is a vertical asymptote. The other one is a hole, so it can't be that. That says two vertical asymptotes. Really should be one's a hole, one's a vertical asymptote. And the graph has no holes because the degree of the numerator is greater than the degree of the denominator. I mean, that's not even kind of true or even possible. That's not, holes don't care about the degree of the denominator and numerator. So there you go. There are the questions on the study guide. And I'll get these uploaded and I'll see you guys tomorrow.